part, we are at section 4.0, impulse force distribution. And what in the world are we talking about? Well, we know that we were able to use the Newtonian impulse force, use the equations of motions we extracted vis-a-vis first and second derivatives by application of Taylor series expansion. We learned how to do that. It wasn't that hard. And just a few lines of code and a bit of an effort and focus. And you didn't need to master calculus or 10 other books you had to open and read. But we discovered that the random impulse forces indeed create shapes and jittery movements that are quite similar to what Brownian fellow reported some 200 years ago. So the point is that mathematicians and physicists, starting from Einstein's time, the paper 905, they would start working on figuring out some mathematical form and shape to this Brownian motion. And it was discovered that displacements, the infinitesimal, very small displacements, of that jitter we talked about, in average is a normal, Gaussian normal distribution. And we want to show you that what you calculated on top of this document so far precisely ends up with a Gaussian normal distribution. Before we do that, let's learn some data structures and structure functions on them. Make a list of anything, in this case, numbers. Select the way you want to partition them. So you want to partition them in the groups of 3. The function in Mathematica is partition. And then run this. And without me explaining to you, you can guess what partition does in this argument configuration. It takes the first 3, makes a list out of them. Second 3, 3, 4, 5. And the third possible 3, which is 6, 7, 8. Okay, and he's able to actually make a list of lists, or list of 3 vectors of each 3 numbers. If you generalize the concept, instead of numbers we use ABCs, and you can see that we start from A0, B0, C0, A1, B1, C1. These are 3D vectors. The same thing, you can convince yourself that it is it is turning these 3D vectors also to groups of 3D vectors. So this is the first vector, second vector, and third vector, similar to the first number, second number, third number. And here we are. You see the same thing. And then for the next group, it goes to A3, B3, A4, B4, A5, B5, and you find it over here. And basically it makes you a list of 3 vectors. Each vector has 3 numbers. This falls under, for those of you who have studied more math and physics, tensors, and I am completely irrelevant for our purpose. Let's go and display this part by using the column function. And what the column does, just turns them into columns, so they're easier to read. Look at your original list. Look at the final list, and you know how this works. Now what we do is that now that we have these lists, we're going to total the amounts. Okay, here it is. We total the parts. Basically, we are totaling the coordinates, say first, x coordinate, x coordinate, x coordinate, a0, a1, a2. When we do this expression over here, we get a0, a1 plus a2, then we get b0, b1, b2, corresponding elements in the vectors get added up to each other, and finally the c is added up. And then you go to the next row, you add a3, a4, a5, a3, a4, a5, you add b3, b4, b5, the same thing you see here, and go on with your life. These would be how we basically add the x coordinates, and this will come in handy for what we are doing next to find the distribution, but for now bear with me. And then what we do is that we call this dv's, okay, and then this expression over here says go through all the dv's, and all the elements in the dv, and give me the first one. I want to see the x, and here you are. You get the x, okay. The first element of every vector. So first element of every vector, you get the first element of the first vector is this, okay. And then you can also ask for the second element. Put number 2 over there. It will give you a second element, which will be b0, b1, b2, and b3, b4, b5. Just to impress you that I know how to program. Yeah, I'm gonna add it here. Make this dy. Okay. And 2. Oh, as I promised you, I did not lie. Okay, now before we go to the major calculations with hundreds of thousands of vectors, let us just try 9 vectors. You remember our famous function f gives us a random 3D vector. For now, make the length 1. For these vectors, actually makes no difference what length you assign. And then go run 9 of these vectors, put them in f list, just we did before. Use the same thing, n equal to 3 for the partitions as we did up here, and partition them, put it in a variable called part, and just turn it into a column and show it to me. Here you are. I had to magnify it to make it smaller so it will fit the screen, but you get an idea. It basically gives you 3 sets of lists. Each list is a 3-dimensional vector, 3 3-dimensional vectors. Here you are. The second member of the list, it has 3 3-dimensional vectors, and the same thing with the third one. Alright, now what we do is that we would like to somehow display these vectors to see how they stack up. So we run this code and look at what we have here. This exhibits 3 random motions of 3 steps each. Let me run it again up here. So we get 3 sets of vectors, each 3. Okay, here you are, much better looking. Sorry if I had to fit this in my recording. So what happens is that the particle at the point of time, we apply 3 independent forces at it 3 times, and it jitters up and goes into 3 different directions as we previously showed you with accumulation. The same thing here, it jumps over here, here, and here, and the same thing with the beige looking color. Okay, so what we are doing is that we would like to compute the average sum of the x coordinates of each one of these displacements to get an idea that this endpoint here at the end of these polylines or polyvectors, at the end of them, what is in average the x and y and z coordinates, and in average what is their distribution as stochastical objects. Okay, so I will repeat that one more time before I go down, but basically you come down here and run the summation of the x coordinates. We had 3 sets of vectors, and these are the summations. You can think of them as averages times 3, doesn't matter. Go back over here one more time. Let's run it from the top. So we repeat again. We get 3 sets of 3 vectors in 3 dimensions, and then these represent 3 Brownian motion jitters, one after the other, by 3 impulse forces. We would like to add these vectors coordinates. So each one of these vectors, we calculate the final point and measure is x coordinates with regards to the pivot point. The same thing for this different kind of looking color here. I think it's what would be the mush piece color. Okay, and the black one over here, black navy blue one over here. We want to calculate the end points where the arrows end. We want to calculate the average of their x and y's and z's, and we assume that where this ball is actually that's where 0, 0 is for ease of computations. Okay, now that we understand what's going on, we go down here and let's do the wild thing here. So we go over here, we make sure every time we make a random vector has length 1. Again, it really doesn't matter much. 3 dimensions. Okay, and this is the function that gives us a random vector of length 1 in this case, d times random real, and then go through the application of this function 400 times as I did before, put it in list and make groups of 3, partitions of 3 as we showed you above. Get the list of those partitions and then sum them up per each coordinate. Okay, and you end up with 400,000 x and y's and z's coordinates separated from each other, summed up on 3 steps of that Brownian jitter itch. Okay, and go ahead and run this. It would do the plots for you, but these plots, this is for x, this is for y, and this is for z. Let's talk about x. Okay, so what is this telling us? If you run your mouse, you can get the numbers. It's okay, you can use them somehow. And on top over here is telling you the mu, the average of the distribution that it fit, and it tells you about the standard deviation or variance, I'm sorry, the variance of this measurement of fitting a particular, what I'm gonna call it, distribution. In this case is I just forced a normal distribution without any thinking. So the fit is very good, as you can see. And what are these bars? These are the histograms, as you know what they mean. If you don't know what histograms are, let us know. We make stuff for you so that you can learn. And for each one of the x and y's and z's, hundreds of, what was it, like 1.2 million coordinates, we were able to get an absolutely a pattern, a bell-shaped pattern, the Gaussian pattern, each time we try it. So let's go try it one more time. Again, 400,000 points, 400,000 vectors, groups of 3, represents 3 steps of Brownian jitter, and then run it again, and we get pretty much the same thing. We get, if we think this is a Brownian distribution, normal distribution, which is Brownians, and we calculate the normal distribution. If this is the case, we find out the average is almost 0, and the variance is 1. Okay. Then what we do, there are algorithms that if you have a distribution as such of x and y's and z's coordinates, that means a large list of x's, large list of y's, and large list of z's, it would tell you the symbolic formulation for how these all fit together as a statistical system. So we go to the same thing we have done before through this whole program. We create 400,000 x, y, z vectors. We go partition them by groups of 3. You can make groups of 4. You get the same result. You can get groups of 30. You get the same result, just the numbers are different. And then what we do is that we do the same thing. We sum the corresponding parts of the vectors, And then for now we focus on the x, which is the first coordinate. And then we run this. What this does calls a function at the end of the day called find distribution. Find distribution. What it does is that it goes and look at all the data you gave it and does a guesswork using some pretty nifty, cool math and algebra and real analysis, functional analysis. And occasionally recently some machine learning algorithms, but we don't care about that. And it issues your report. I ask only for one best fit on the top of all possibilities. We come down here and we go and run this keys/report, which keys will give us particular name of a distribution we found. And here we are. Let me run it again so you can see. So it says it's a normal distribution, which is what I added up here. I forced it, believing there's a normal distribution in my plots. But it tells you that it is a normal distribution, indeed. And it has an average of nearly 0, 0.004 of a point. And it has a variance of almost 1. So what does this actually really mean? Normal distribution has that Gaussian formula that you're aware of. Let me see if I can bring that formula up. I forgot to do that. Sorry if I run something on top of the window here. My apologies. I'm going to move it off there. So I'm going to do the normal distribution. I should have done this earlier. Sorry for that. And here we are. Normal distribution is the following formula you can grab. Here we are. And let me magnify this so it's a little bit easier to read. Oops. Magnify. Let me magnify the symbols twice so you can see better. Okay, here we are. I think for all of us this is easier to read. And here you have the formulas in terms of mu and the little sigma. And you can see an exponential e to the minus x minus the average, in this case is 0 to the power 2 divided by 2 times sigma squared, and then funky 2 pi, square root of 2 pi, and then the sigma again. Okay, and what happens here is that now the 400,000 vectors that we generated vis-a-vis the impulse force has a symbolic identity that ties them together, not in terms of their coordinates, in terms of the probabilistic distribution or statistical distributions of their coordinates. That means that that impulse force is creating a statistical or stochastical process or object, an object that varies in a certain specific way, and that certain specific way has the distribution, normal distribution, which is the Gauss's formula, the exponential like this, and from that we can extend the mu and sigma, know our variance and our standard deviation from that. So basically, this formula over here, if you plug in the numbers for mu, okay, here we are. If you plug in the numbers, which I can do shortly if you're interested, and we plug in the sigma for its number, then we are able to see that there's a formula that applies. And as a matter of fact, I'm going to do it right now. Sorry, it's a little bit funky improv here, but improv is good. That means we are enthusiastic about things we learn and things we think about. When people are very scripted, that means they are not interested. They just want to just put something on the blackboard and go home. and do something else with their lives, each to his own. Okay, here we are. I replace this is slash means replace all, slash dot, I'm sorry, replace all. We take the mu, the average, and sigma, and we basically have a nice formula over here. And this formula ties the x coordinate of our Brownian motion displacements vis-a-vis this formula that you see over here, and scaled by this factor. It says that the distribution of the x and y and z coordinates are normal distribution, Gaussian distribution, and that is basically how Brownian motions, Wiener process or Brownian motions, are algebraized, turned into mathematical structures in any of the books you see. And now you know that without you reading those books, without you have any idea about the detailed physics of Einstein's paper of 1905, without you understanding differential equations, all you needed to know was that large investment of money into calculus, one semester, one single variable, Taylor series expansion. That's all you needed to know. And vague concept of the derivatives. First derivative is velocity, second derivative is acceleration. And here you are, you're able to extract with all these computations visually and analytically and animate Brownian motion vis-a-vis the impulse forces that last a very short period of time. Okay, so I will leave everyone to spend the rest of the week to admire me for my incredible presentation tonight, and best of luck to all of you. And we will be off doing more of these videos, hopefully a little bit more organized. This is the first try. Good night. Bye bye.